I'm going to be reporting today on a project we've been working on for about a year, still well underway. This is one that, in addition to myself, Mia Lockhead and Peter Lee, a couple of students from Stanford, Mia's in the audience here, and Quanxi Zhang, former student and was with the Sim Center as a postdoc, now at University of Cincinnati, working with us on this project. So it complements the previous talk we heard. It's really drilling deeper into trying to bring high fidelity models of bridge performance into transportation networks. So we're not looking at the network itself, we're just going to look at kind of modeling bridges, tying that into kind of the hazard analysis part. The outline today, one of the things we're doing in this project is really trying to utilize and help develop further some of the Sim Center software, so I'd like to briefly introduce that. We'll talk about using surrogate models as a way to, after we train them on high fidelity bridge models, how we could use surrogate models to deploy them into large transportation networks, and then look a little bit at the regional modeling. So just a few words on the Sim Center. This has started a few years ago. It's headquartered here at Berkeley, a number of schools participating. This graphic is really a brainchild of Frank McKenna and Steve Mahan, kicking off the Sim Center. The idea is to really encapsulate different kinds of software tools with pre and post processors to then create computational workflows, which is shown in this diagram here. Could go from kind of describing the inventory of facilities, the hazards, characterizing, propagating that through doing a response analysis, and then finally looking at damage and impacts and recovery. So it's essentially work that Pierre's been working on for years, and underlying this, of course, is transferring data and characterizing uncertainties with our kind of the Pierre framework equation is still living strong after many years. So what the Sim Center's been working on is putting together a number of software components, these different modules that go from kind of the hazard to the response simulation, damage, and recovery, having these kind of collecting these, and then we've built them into a number of desktop applications, and I'll describe a couple of these that we've been using. But then within the NEARI, and this is working with folks at the Advanced Computing Center down at University of Texas, Austin, to build this into an ecosystem where these could run on high performance computing, they access through your desktop, they could tie seamlessly into online databases, so the Pierre Ground Motion Database, National Bridge Inventory Database, and so forth, and also take advantage of high performance computing and also the data storage that's available through NEARI, and just really facilitating more and more researchers to be able to run these workflows, and also to start sharing data. I think as we do these regional simulations, it'd be great if each one that we do, we could share the data that we collect for that regional simulation with another group who could do something different with it. So the three tools that we've been using, one is called QuoFem. This is one that kind of combines uncertainty quantification tools with finite element software such as OpenSeas or other. This can do uncertainty propagation. It can use optimization to calibrate computational models to experiments. And then what's important for the project today is surrogate modeling techniques are built into this. The next tool, EEUQ, that kind of takes the features of QuoFem and combines them into tools that are going to tie into characterizing the earthquake hazards and ground shaking. So this is where we tie into OpenSHA to kind of characterize hazard effects, target spectra, and then pulling ground motions from the Pierre Ground Motion Database, again, to do that seamlessly. And finally, this R2D, this is looking at building all of these tools into regional simulations. So in addition to kind of working on our research, we're really making an effort to kind of test out and further development of these tools so that they could be available for others to use. Next, I'd like to talk about some of the work we've been doing on surrogate modeling. The three general types of surrogate models we're looking at, the first one is kind of at the top, that's kind of a response surface type, where basically you have a parametric expression where you're fitting it through a set of data. This could be n-dimensional data. Some of it's input for your analyses, the structural characteristics, the hazard, and looking at response, but fitting it through parametric surfaces. The next one down, Gaussian process models. Sangri Yi spoke about this yesterday in some of the Sim Center tools. Here we're taking the data and trying to infer, put kind of Gaussian distributions on the different parameters, and then sampling from those distributions to estimate the response. And then another one is this probabilistic learning on manifolds, where it's kind of looking at data. It's not trying to fit distributions or functions to it. It's trying to look for patterns in it and filling in more of that data. And the two that we focused on, really the effort's been on the plum, but also a little bit with Chef Ida, which is some previous work we did. We're doing detailed models of bridges. This actually builds on a prior peer project where we developed open seas models, and in particular built-in models to pick up reinforcing bar fracture. And in particular, we were looking at the effect of the time of earthquake duration. So we took a number of ground motions that had similar spectra, but different durations. And a key aspect of the duration is kind of the low cycle fatigue and fracture, and demonstrating how this open seas model with the new functionality could kind of pick up those effects. So that's kind of the engine that the detailed model will be running and training these surrogate models on. In terms of looking at the ground motion, we're looking at, of course, the intensity of ground motion, also the spectral shape, and here we're using something called SA ratio. This is really builds on what Eduardo Miranda looked at, SA average, looking at SA values over a certain period range that picks up the spectral shape, and then finally also looking at duration. So we want to be characterizing our ground motion in terms of these kind of three metrics, if you will. We're going to be doing incremental dynamic analyses, which in a sense violate the ground motions. We take one ground motion and scale it up, as opposed to doing, say, a multi-stripe analysis that would be more true to the hazard, that is picking different ground motions at each intensity. Some of the surrogate modeling techniques are then going to adjust the response for these ground motion effects. So the Chef Ida, and this is one that worked on with Jack Baker and Quanqi Zhang. It's been kind of written up in a paper, but basically we're taking the detailed model, we're going to do an incremental dynamic analyses, and the ground motions we're going to pick for that, we call it a gridded set of ground motions. We're going to look for a bunch of ground motions that have a range of spectral shape, and then also have a range of duration, and this is a grid of 7 by 7, so 49 ground motions that sample that large space. Conduct incremental dynamic analyses of the bridge, and you see the Ida plots, the spaghetti plot shown on the right. We could then slice through that, looking at, for example, some of the Caltrans damage states, the CDs that are shown there, or looking at collapse, kind of pulling out those data sets, which then we need to kind of relate those results back to variations in our structural model, could be design parameters and the ground motion parameters. So the Chef Ida is one where we'll again use this response surface. So if we want to look at collapse, or if we want to look at another damage state, we'll kind of target that and kind of fit a surface through. So if we're looking at collapse, we'll look at the SA intensities that cause collapse. This graphic on the left is shown that plotted with respect to spectral shape and duration. And the idea is then when we get to a specific site, we could then kind of probe this response surface for the spectral shape and duration characteristic of the site and the intensity that's causing collapse. So the CDFs that are shown in the upper right, you can see the blue plot is the original data. Those three colored plots are how we can tune this site for, say, a site in San Francisco of different soil class that would have different, spectral shapes, or one in LA. And then the plot in the CDF in the lower right is showing some of the validation where we'll do a very detailed multi-stripe analyses with even more ground motions. That's kind of the ground truth, and to see how well this Chef Ida is making that prediction. So the idea is that we're going to take bridge models and we're going to characterize them with different ground motions. Then we're going to have surrogate models. I'm going to switch gears and talk with what we've been focusing on this year, which is this probabilistic learning on manifolds, another type of surrogate model. So we'll talk a little bit about that. We've also done multi-stripe analyses, and these are used to, again, validate that model. And then we'll finally look at the end of today's talk, looking at putting those into regional simulations. So in terms of the training data that we're looking at, these are the detailed open seas model of the bridge. We're looking at having 6 kind of structural parameters, the diameter of the column, slenderness ratio, and so forth. We have the 3 ground motion parameters, the intensity, the spectral shape, and the duration, and then we have 6 response parameters. So in total, there's about 13 variables that we're keeping track of. We actually do 12,000 realizations of 600 different realizations of structural properties, and then taking those through incremental dynamic analyses for all the different ground motions. So we have this large data set that we then want to interrogate for putting a bridge with certain characteristics at a certain site with different hazard properties. So this is just a snapshot of some of the results that we get, and it gives you a little clue in terms of how this plum model, the surrogate model, is working. So the scatter plot that's shown on the lower left of this slide, if you look carefully, the blue dots there, those are the results from our incremental dynamic analyses. And this is spectral acceleration versus a demand parameter, say curvature in a column. The green dots that are shown there, that's this multi-stripe analysis. That's what we want to, for a specific site and different bridge design, that's what we want to sort of be targeting, if you will. And we're running, there's still ground motion, so there's still uncertainty in that plot. But then if we take for the target site, if we take measurements of, say, the mean and the standard deviation, what Plum does is it fills in, and those are the yellow plots, the yellow points that are shown there, it fills in additional data points there. And then when we want to then sample that data space, we're just basically sampling out of that yellow. And the two CDF plots, the one shown on top is looking at the, that's going to be for different spectral accelerations for our site, how well we're able to, from the blue, the IDA values, that's the original IDA set that we have there, how we're able to get the Plum model to match this multi-stripe analyses. And then what's important is the CDF that's shown on the right is looking at the response. In this case, we're looking at the curvature of a column. So the idea is that we want to train that, or have that Plum model be able to make those predictions. This is for a particular, putting a bridge of a certain characteristics in Bakerfield. Shown on the left, it's under a 500-year return period. Shown on the right, it's under a 2,400-year return period. So it's the same training data set. Here we have different multi-stripe analyses, and here the Plum model, when it's tuned properly, is going to give us a quick way to kind of estimate that response without rerunning the OpenSeas model. So basically, the process we've been going through is developing first this training set of data. These are the 12,000 analyses of OpenSeas models. Then making the Plum predictions, so that's where we're kind of filling in using the Plum algorithms with these additional data points. Now that the Plum process has some hyperparameters that have to be tuned, so then we're also calibrating those. And so for these, we have to go back to the ground truth data from multi-stripe analyses and selectively tune this. And the idea is if we do that properly, then we could take that tune model and apply it to other bridge locations and other hazards, sites with longer duration, different spectral shapes. And then what we've been doing, working hard though, is to validate that by doing multi-stripe analyses at many of those other sites to see how well this Plum model is working. And the devil's in the details on these things. There's these things called hyperparameters, which if they're not tuned well for your model, you get results such as shown on the left here, where we have the blue, again, that's the training data. The green, that's the target data that we want. And the orange, that's the Plum data. So in this case, we're neither matching very well with the Plum algorithm the intensity of the ground motion that we want, and nor are we getting the right results. But the idea is by going through this optimization calibration process on these tuning parameters, the idea is that we get the better fit such as shown on the right. Okay, and finally, that's just a snapshot of a few of the variables that we'd be looking at. And again, the one on the top here is looking at the intensity of ground motions. That's part of the data set. Down below is looking at one of the response indices. The data set is, again, 13 variables in 13-dimension space, so we could look at any of those. And so for the validation, then we've been going systematically for putting bridges at different sites with the ground truth multi-stripe analyses, and then doing plots like this where we're looking at the 3 ground motion parameters, how well are we matching those, the model parameters that we're shooting for, how well does the Plum model match that, and then finally what's shown on the right side is the important thing, the response quantities. And if we get this right, then we could have these, it's basically taking the place of our old fragility curves that you might have from HAZUS with bridge characteristics. Here we have one that's picking and tuned to these higher fidelity models. Okay, and I'd like to shift gears a little bit and talk about, we're still in the process of kind of tuning, validating those models, but then looking ahead of building them into the regional simulation platform that the Sim Center's put together, R2D. So again, these are taking the surrogate models into these regional analyses. So what we've been doing for a trial study here is the bridge model we've worked on in the past. It's for a single pier with a 2-span bridge. And then we looked around the Bay Area and going to the National Bridge Inventory, pulled out bridges that kind of fit this general category. Those are shown on the black dots on the graphic of the regional model on the left. And for testing purposes, we just pulled out 12 of those which are ones built between 1970 and 79, so, okay. So that's going to characterize, say, the tie spacing and so forth. We also tried to pick them up at different sites with VS30 that's going to vary the ground motion. And then for response simulation, we're currently running open seas models for those sites. That's kind of the ground truth, if you will, for a certain scenario. And then we could apply the Plum model and compare and see how the advantages of that, how accurate it is and how it speeds things up. In the process of doing this, as we dug into the R2D, the hazard model that SimCenter's put together as part of R2D, there's different capabilities there. We're interested in looking at one for specific earthquake scenarios. And underneath that, you can go in and pull earthquake scenarios. They could be, you could pull in hazard information from an old shake map if you'd like. What we're doing here is we want to pick a certain scenario, a certain magnitude earthquake. We're going to look at the Hayward scenario. What R2D does in the hazard tool, it ties right into OpenSHA, where we could go to USURF and we could look for a fault rupture that's in the thousands or tens of thousands that are in USURF that match that Hayward scenario, use ground motion models to make estimates of ground motions around the area, get target spectra for those, and then match ground motions to those if we want to do nonlinear dynamic analyses, or just taking the spectra and using things like the surrogate model. So this is an example of the work there. It's, again, going to that Hayward scenario. We're pulling one rupture out of the USURF database, and then what we're able to do is pull out realizations of that, which are going to be spectra at all the different sites that respect the VS30 at the site. And here we're taking advantage of some of the work Jack Baker and others have done on looking at correlations of the ground motions, across the periods of a structure, kind of like conditional spectra, and then also spatial correlations. So we're in the process of working on that. So just in terms of summary and next steps, we're short on time, so I won't go through all of these, but I think one of the key things we're trying to do in this project is to really streamline this surrogate modeling approach that is for researchers to look at the method and help provide guidance on how one can take this tool of Plum or a Gaussian process model, go through a systematic process to train and validate your models. So that's kind of on the research side. And eventually we'd hope that then we have a whole library of different surrogate models that then folks who are interested in applications could then apply these to look at, like the previous study. If you want to look at transportation network and how it affects transportation times and what's the economic, to take advantage of these kind of high fidelity models within those simulations. So thanks for your attention.